All right, so in this next lesson, we are going to talk about data wrangling. This lesson and the one after this are both focused on data wrangling. Um, at the end of this lesson, you should have a sense of why do we need to manipulate data? What is the tidyverse? And what can you do with dplyr, which is a package within the tidyverse? And what is piping? So again, this is going to be a lot of information, but the intent is to just expose you guys to what is possible and what you can do with R. So in the R basics lesson, I had you load the tidyverse, install, and then load the tidyverse, and import some data. So I want to spend a few minutes talking a little bit about what the tidyverse is and why it's so important to R and you as budding data scientists. So the tidyverse has only been around for maybe about, I want to say 7 or 8 years now. But what it is a set of packages that work in harmony because they share common data representations in design. And all of these packages together are really meant to facilitate the entire data exploration process. And you can see this process in this graphic here, where this is a typical workflow you'll do in RStudio where you're working with data. You'll import the information, you'll clean it up, and then you'll start this understanding phase where you're exploring the information that involves plotting the data, modeling the data, transforming the data. And this is all an iterative process that is not, linear from start to completion. But when you're done with this understanding process, you then communicate those results to whoever you're working with or what you want to do with the data. This graphic is from the book R for Data Science. This is an excellent resource that I read a couple years ago when I first started learning about the tidyverse. And so a lot of the content is from this book. So I really encourage you to have a look at this if you want to learn more. So to start, we already installed the tidyverse. If you're on RStudio Cloud, this should already be there. If you're using your own RStudio project, you should have installed this prior to the workshop or in the last lesson. But after it's installed, we have to load the package. So we do that again with the library function. And again, we have to do this every time we install, or rather we use R, because each time you start a new R session, R doesn't know what packages you want to use. So that's why you have to do the library there. So I'm going to put that into our live script just to show you what happens. So I'm going to restart R. So I just started a new R session in RStudio. Doesn't have anything loaded. There's nothing in my working environment. If I load the tidyverse, I should see some messages like this. Totally okay, totally normal. This is just telling you what packages it loaded with it. So what's unique about the tidyverse that is different from other packages is that the tidyverse is a collection of packages. It's kind of like a meta package. So that's why it spits out all this extra stuff in the console saying what it loaded. There's some conflicts that you can, for the most part, ignore, and then warnings, which are basically just saying update your version of R, which I need to do. But as long as you don't see any errors, it's loaded just fine. And these are the core packages that it loaded when he loaded the tidyverse. So we have ggplot2 for making plots. We have dplyr, which is what we'll use a lot in this lesson. We have tidyr for making data tidy, which I'll talk about in the next lesson. We have reader for importing data. We have per for functional programming, and we have tibble, which is, for all practical purposes, like a data frame, which is a two-dimensional data structure that I talked about in the last lesson. So I'll move on to data wrangling. So if any of you have spent any time working with data, you will realize that the majority of your time, if you have a question about a data set, is getting the data into a format that you can use for whatever question you want to address. So data wrangling is this process of getting the raw data into a format that works for your analysis or question. And I kid you not, you will spend probably 90% of your time in this wrangling process when you're working with data to answer a question. So it's not necessarily a fun process. I think it's fun, but I'm kind of a nerd. But it is a time-consuming aspect of data analysis that will take up a lot of your time. And so dplyr, as well as tidyr, which are, again, two packages that come with the tidyverse, will facilitate this entire process. So this is the schematic that describes the whole data analysis workflow, and the wrangling part is the portion that begins with importing the data, tidying the data, and transforming the data. So when you think about wrangling data, I guess always think about the questions you want to work towards. And so what is your analysis you're trying to do? What plot you're trying to create? And then how do you get there? So always realize that wrangling is based on a purpose. You're working towards something. And to get to that purpose, you should think about answers to these questions. So what do my input data look like? What format are they in? And what should my data look like for the analysis I'm trying to do? So what sort of manipulations do I need to do before I can make a plot or before I can create a model in R? So it's always good to look at your data when you import it to start thinking about those questions. Now, some of the things you'd want to do to your input data to get to where you want to go are things like selecting specific variables in your data set. So are there columns in your data frame, which is that two-dimensional data structure that you care about? Or are there observations in that data set, in other words, rows across columns that you want to filter by that are important for some reason? Or are there new variables you want to create in your data set? So do you want to manipulate one of the columns to create a new column that has some new information? Or do you want to create something totally new from scratch? Do we want to change the names of variables? Do we want to sort by a variable? Or do we want to summarize the data in some way, conditional on some characteristics in the data set? So these are all things you can do with dplyr. dplyr will give you the functions to do this, and they're all named in a way where the functions are kind of like verbs that are literally telling you what it's doing. So you can select, filter, and rename, and so on and so forth. These links here are just some links that are helpful for understanding dplyr. Perhaps the easiest one to look at right now is the cheat sheet. I didn't mention in the last training, but RStudio has a ton of cheat sheets available. This is just one of many, focusing on dplyr and tidyr. So this is often a good resource to just not only understand the functions that are in dplyr, but what they're doing as well. So I encourage you to look at that as a first stop for dplyr. So I'm going to import our fish data set. This is a data set of over 30,000 catch records in a part of Tampa Bay that's called Old Tampa Bay. So it's a large data set, it's kind of cumbersome, and so we're going to want to do some wrangling on that before we move forward. So this is something that we should have done in the last lesson, importing the data. So I've loaded tidyverse. I'm using the read CSV function to import this file in the data folder in my working directory. There we go. We get some information, just says, these are the things I imported. These are the columns that you've imported. These are the types of things that they are. So these are numbers, these are characters, so on. So just because you see text on the screen doesn't mean it's wrong. It just means this is R telling you that I've done something. And we don't see any errors, so that's a good sign. So I'm going to look at the data set. I'm going to actually type this out so I can look at the dimensions of that. I can look at the names and the columns. What else do I want to do? I'll view it in a second, but let me just show you. So this is, if I run dim, this is basically just telling me that there's 2,800 rows, 12 columns. If I run names, these are the column names. So there's an object ID, reference, sampling date, year. A useful function is head. This will give you the first 6 rows in the data set you've just imported. Or if you want, you can look at the whole data set with view. And this will give you kind of a spreadsheet style way to look at the data that is very handy. You can arrange rows and your viewing and so on. So we always want to look at the data before we start wrangling so we know what it is. So this is, again, the first 6 rows, object names, what the values are in the rows, what they are. So a double is a number, character is a character string, date's a date object, so on. So this is our starting point. Oh yeah, one other useful function is the str function. This is called structure. This gives you a very quick overview of what the data set looks like, kind of a nasty looking print output in the console, but it's once you wrap your hand around what it's telling you, it's quite handy. So this says it's a tibble, which is kind of like a data frame, 2,800 rows, 12 observations. Here's the number of, or here's the columns, their names, what the column types are, numbers, characters, dates, so on. And then this stuff down here is just a little extra information about attributes. So let's begin by selecting some columns of interest. So remember, maybe we don't want all of the columns in the data set depending on what we're trying to do. So I'm just going to show you some examples of selecting some columns of interest with dplyr. So if I go back to our studio, paste that in. So here I'm saying, use the select function from dplyr, use the fishdata object, and then select these 3 columns. So remember there's, according to this, 12 columns in the raw data set. So I'm going to select the sampling date, gear, and pinfish columns. Okay, cool. We can look at that. And now you see that we've removed everything but these 3 ones we wanted. So that's pretty straightforward, just removing columns that we don't want. What's also useful is sometimes if you use the minus object, this says remove that column as opposed to let me keep that column. So if we want everything but these 2 columns, object ID and X date, we can use that. Another useful one is the matches function within select. So I'm just going to do this one right here just to show you. What this is saying is select all columns where there is a letter C in them. So if you have many, many columns, you can use that. And here, if I show you the result, we'll see that, yes, this worked as we thought. There's a C in that column, there's a C in that column, there's a C in that column. So there's a lot of little tricks you can use with selecting that are helpful sometimes. So that's really straightforward. That's just basically removing rows, or I'm sorry, removing columns we want based on the analysis we're doing, because there's oftentimes a lot of extra columns that isn't information that's relevant to our question when we're doing an analysis. So the next one to think about is filtering. So this is kind of just like selecting, but instead of selecting columns, we're selecting rows. And this is called a different name because we can't, have one function that does more than one thing. So we're calling this filtering. But think of this as a way to just remove rows in your data set across columns based on some criteria. So in this first example, I am going to filter all of the rows where the number of pinfish in this data set is greater than 30. So copy that into my script. Here's the filter function, running it on fishstat, my raw data, and I'm saying get the rows where all pinfish is greater than 30. So if I run that, I'm going to show you what this did. So first of all, let's look at the raw data. So here's everything. Here's our pinfish column. We see that there's a lot of variability in the catches. So these numbers are how many times or how many pinfish were caught on this date at this location. So this date 0, this date 54, this date 80. So we see a large range. So maybe we want to remove all observations in this data set where pinfish catch was low. So if we look at then the one I just filtered, with the view function that'll pop up. Now we have a lot less rows in our data set. So we now have 442 as opposed to 2,800. And if we go over to the pinfish column, we see that, oh, now all of our catch data is above 30, which is what we told R to do. So we're just sort of filtering all of the observations, all of the rows across the columns where pinfish catch was below 30. So now we have high catch numbers for pinfish. So that's the simplest way to do a filter. We could use another filter that's kind of like an equality. So here I'm saying, let's use the gear column, which is the sampling gear that was used to collect the fish. And I want to get observations for all of the sampling gear, or all of the observations where the gear number 20 was used. So if we go back to our raw data set, we see essentially there's a lot of different gear types. Gear 20 is a really common one. Maybe we want to look at catch results for just that gear type. So I'm going to run that, view it. Okay, and now we see that we have all of the observations corresponding to gear 20. So you'll notice that this equality sign is 2 equal signs. That you got to be really careful when you're doing an equality, when you're selecting, to make sure you use 2. Otherwise, it won't work. It's just oftentimes first-time R users are tripped up by that. Okay, so if you've ever done any kind of structured queries in other databases, if you're familiar with that, R has all of the standard queries that other database selections might use. So there's greater than equal to, less than or equal to, not equal to, which is the exclamation point followed by equal, and then equal. And so conceptually, what that would look like is, these are all of the ways we could filter data. So we could have all instances where everything is equal to some criteria Y and not equal to X, so the exclusion there, everything equal to X, everything equal to X or Y. So this horizontal bar is the OR operator. Everything equal to X in Y, right there, and so on and so forth. So you can combine any of a number of filtering statements in a way that is sort of congruent with these Venn diagrams. So the first examples I showed you were just simple things like, let me filter all rows where pinfish is greater than 30, but we can combine that into more complex statements. So in this example, I'm telling R to select all rows in this data set where pinfish catch is greater than 30 and the catch is less than 100. So we can combine these things with the AND operator there. So if I run that and I look at that data set and I go, so it's a much smaller data set to start with, only 215, but if I go over to the pinfish column and I sort it, I see that the smallest one is 31, so above 30, and the largest one is 99. So this just by looking at the data, we could tell that our filter worked as intended because the column for pinfish meets the criteria that we told it. On the other hand, if we used OR, this is basically saying, give me all rows where pinfish catch is greater than 30 or pinfish catch is less than 100. So we can run this and, okay, it ran. Now we have, look at our new data set. So this type of filter is not that helpful because we're just saying select all of the rows because it meets this criteria. So you're going to say, I want all the rows where pinfish are greater than 30 or pinfish are less than 100. That includes rows with 0. That includes rows with 4, rows with really high numbers. So this data set that we've just filtered with the OR is the same as the raw data set. So just to show you how that distinction between and or works in this case. Now you would never do a filter like this because it doesn't make sense, but I'm just trying to sort of impress upon you the difference between and versus or. Yeah, so this is an example where or does make sense. So here we're filtering it by gear types equal 20 or gear type equal 5. So this is a subset where these things are mutually exclusive. So you're going to get a data set that makes sense. If you did gear equals 20 and gear equals 5, you're not going to get any data because there's no instance in this data set where both of the gear types were used. Just to clarify that. Okay, the last thing I want to show you is mutate. And this is a function that's helpful for creating new columns. So oftentimes we want to create a column that is a derivative of another column. So mutate says, from the fishstat object, I want to create a new column called bluefish P100 that is equal to bluefish divided by 100. And so this is a little bit different than the previous function. So there's 2 pieces of information we need to tell it, actually 3. So we need to tell mutate what data set we're doing this on, but we also need to give that new column a name. So I made this up, bluefish underscore P100. You can call it whatever you want. So blue, mutate, whatever, doesn't matter. And then there's equal sign that says what this new data column is going to be equal to. So bluefish is an existing column in the data set. So if we look at head fish stat, bluefish is right there. I basically said I wanted to make this new column a proportion of the existing column bluefish. So I'm dividing it by 100 in this example. So if I run this and I look at the result, dplyr mutate, just save that for you guys. There's a new column all the way at the end here. I'm going to sort it by value so we can see what it's done. This basically said, I'm going to take this bluefish column, divide it by 100. So a trivial example, but just showing you that it faithfully divided all the values in bluefish by 100 to make that new column called blue mutate. So pretty simple there. We can also do something useful by converting an existing column that's a number into a category. So in this example, I'm saying, this is kind of a complex statement, but I'm doing the same thing. I'm using mutate on the fishstat object, and I'm making a new column called mullet cat. So mullet category, it's kind of an informative name, but I'm basically saying, in cases where mullets, this is the existing column, are less than 20, so I'm using an if else, I'm going to assign the value few, meaning there's not a lot of mullets. Otherwise, give it a value of many. So if you're familiar with if-else statements, this should make sense. If you've never seen an if-else statement, this is a way to logically assign values based on some criteria. So if mullets are less than 20, give it a value of few. If otherwise, give it a value of many. So this is, again, complex because we have functions within functions. If else is a function by itself. But when I run this, I can show you what that result looks like. Okay, so dplyr mutate 2. Here's mullet category, so few, a lot of fews. So if we look over at mullet, here's a lot of zeros. So these are all less than 20, so that makes sense. These are all given the few category. I know there's some many. Okay, well, I'll just sort that to see where we're at. Okay, so it turns out they're all fews because the highest value we see is 5 in this case. So we'll just, for fun, change that to mullets less than 3 so we can see more of a distinction there. So view that one. Oops. So again, we still see a lot of fews, but if I sort by mullets, okay, so now we only have 3 instances where there were many based on our criteria because these are observations that had more than 3 encased 5. Okay, so that's just sort of mutate in a nutshell. Again, it's usually just deriving new columns from existing columns. So in the first 2 examples, I derived blue mutate from bluefish, an existing column there, and then mullet cat from mullets. If I want, I can create a totally new column called new column, just totally undescriptive name there. But say I want to just give it a number. So this could be a placeholder for something. Who knows why we'd want to do this, but just to show you what this does. Now we have a new column. I'm actually going to do the view there. So we see this new column on the end where we only gave it one number in this case, but it assigned that value to every single thing in the row, or every single row in this column, just to show you how that works. So you can make columns with mutate without deriving them from an existing column. That was really the only reason I wanted to show you that. Okay. So that's mutate. 2 very quick functions I want to show you from dplyr is arrange and rename. So arrange is kind of just like the sort function in Excel, if you're familiar with that. It's very simple. Basically, you just say, I'm going to arrange my data object and then tell it which column to arrange it by, in this case, sand sea trout. So this will just sort all of the rows by ascending values in that column. Looking at dplyr arrange, now we can see sand sea trout is arranged from smallest to largest. So we go all the way to the bottom and we see, oh, the highest value there. I typically don't use arrange as part of my analysis workflow. It's more just to see which values are highest. And of course, there's a lot of ways you can do that in R outside of the arrange function. So again, I don't really use that function very often, but it could be useful to some of you. And then the rename function is, you guessed it, a way to rename columns. So maybe some column names are tedious, they're long, or they're using atypical expressions in terms of having spaces or numbers in front of them. So we might want to rename a column just because if we're typing that column name a lot, we can name it something simpler. So very simple, rename the data set I'm working on, the name of the new column that I choose, an equal sign telling it which column to rename, and the name of that column. So dplyr rename, and if I look at the names of the data set using rename, made a typo there. There we go. We see that Snook has been replaced with that new value for the name. So pretty simple there. One last thing before we start our first exercise that I didn't mention is that you see that some column names I'm surrounding with backticks, others I'm not. So when I call column names with dplyr, like Bluefish wasn't surrounded by backticks, Mullet didn't have backticks. So a backtick is what you have to surround column names if they have a space or if they are starting with a number. So these are atypical values that R typically doesn't, or that it doesn't expect when you're defining column names. So in order for R to understand what you're actually telling it, you have to surround it with these backticks. So just for sake of example, I can show you what happens when I don't do that. So right now, RStudio is already giving me an indication that something's not right. But if I send that to the console, it says, oh, unexpected symbol. So this is just R's way of telling me, I don't know what you're trying to do. So there's a space in this column name, and we just take care of that with backticks. And again, if there's not a space, we don't have to do that, but it doesn't hurt regardless. This will still run. There we go. That'll still run just fine. But just realize if you have strange column names, sometimes it's easy to overlook that and you have to use the backticks. So let's start our exercise. What we're going to do is basically run through a few examples of the functions I just went through, selecting, mutating, and filtering. Or actually, there's no mutate here. We're just going to select these columns of interest. We're going to filter by a specific gear type, and then we're going to rename a column with a different name. And so if you get lost or if you want to cheat, you can see the answer here, but I'll give you a few minutes to go through that. And feel free to look at the examples above on your own computer to figure out how to use some of the syntax for the functions. So I'll shut up and I'll give you 5 minutes on the clock to do that. All right, that's 5 minutes for exercise 4, and we are doing good on time. So I will walk you through what we did for this exercise. And Gary, I did see that request in the chat. I'll get to that in a second. Let me just copy that. Okay, I'm going to write a comment, say this is exercise 1. All right, so I wanted you first to select the columns reference, sampling date, gear, and sand sea trout. And remember, sand sea trout had that space in there, so we had to surround it with backticks. So looking quickly at fish stat, again, 2,800 rows, 12 columns. Maybe we don't care about all of them, so we're going to select 4 columns of interest. We're going to assign it to this EX1 value, and we could see it in our environment there. Also, a little short, quick tip here. Anything in your environment that's a data frame or a tibble, you can click on it and it'll show up in the view pane here. So I was typing those view functions earlier to make that pop up, but you can click on them if they're in your environment to make them pop up. So I'm just going to close all of those that I had open. So that's it. It's the same data set, 2,800 rows, the 4 columns we wanted. Then we're going to take that EX1 and filter it. So if we did this on just fish stat, like that, we would still filter by gear type equals 20, but we would have all 4 columns, or I'm sorry, we would have all 12 columns there instead of just the 4 we selected. So we're going to put in EX1 there because we just created it there, and we're going to create it. So looking at the first 6 rows, now we have, again, the 4 columns, but only gear type equals 20. And then we're going to rename the date column with this new EX1 object. Do that. Look at the first 6 rows, and there we go. Date has a new name. So what I've done here, I'm going to save that for you guys. So I've sequentially created a new data object with each step, and I keep rewriting it over and over so I can keep progress of the steps that I did to 1, select, then filter, then rename. This is a pretty common workflow in R. That, there's nothing wrong with this workflow, but in the next session or next lesson before the break, I'm going to tell you about a different way to do this that is a little more handy. But at the end, you combine all of these functions into one by just rewriting that example object over and over, starting with fish stat, then going to EX1, EX1 again and again. So there was a request for me to clarify why I was typing things in the console and not in the live coding. For you guys, I need to be more vigilant to just put things into the live coding so you guys can keep track of it. But generally, for me in my typical workflow, I don't write anything in my script that I don't necessarily want to save. So like if I'm just doing a quick, let's look at the first 6 rows, and I don't necessarily want to save that as part of my workflow to creating or wrangling a data set, I just won't put that in the script. So that's why I was just typing it direct in the console. The general philosophy is that a script should be a standalone set of commands to accomplish some task. And this, looking at the first 6 rows with the head function is not critical to creating a final data object, in this example, EX1. It's just sort of an intermediate step so we can just verify to ourselves that, you know, what we've done is what we told R to do. So it's totally up to you if you want to put that in your own script when you're doing your own workflows, but just it's my personal preference not to have, you know, these little functions in here that are just checks for what I'm doing. Not saying it's bad to check what you're doing, but I just don't save it as part of my typical workflow in writing scripts. But I'll try to keep everything in there for you guys as you're going through the lesson. So hopefully that's clear explaining that. So in this last 10 minutes, I want to talk about this concept called piping, which is a way to make your data wrangling workflow a little more efficient. So I want to start with this really gnarly example where this is, I forget where I got this example. I found it somewhere on the internet, but someone's example of data wrangling using functions from the base R installation. So functions not from dplyr. So here they're creating a new object called cropdat by filtering by some rows. They're selecting columns, they're renaming things, they're doing some filters, all in base R, but they're doing a lot of things in here, and it's not abundantly clear to me. And like I said, I've been using R for a long time. I can't read this code very well. It's kind of messy. They're creating a lot of intermediate data objects when they're doing this wrangling to sort of clutter up their working environment. So this works for what they're trying to do, so it's not technically wrong, but it doesn't necessarily follow sort of best practices for writing code. It's hard to read, you're creating a lot of intermediate objects, and it's just, it's not an efficient way to do data wrangling. So we're already, doing a lot better than this example because we're using dplyr to accomplish tasks where the functions are sort of set up as verbs that tell you what they're doing. So it's very easy to quickly tell that, we're selecting things or filtering things. But I haven't told you how to sort of link those steps in the data workflow together to create one complete wrangled object. So I'm going to show you this example, and this is very similar to the exercise that we just did. So we're not going to use pipes here. This is, you should know how to do this so far. So we're just creating something by selecting columns from fishdat. Here's bad example. We just created that, and we're going to filter bad example by common snook where catch was greater than 25. So we only selected 2 columns, and we're filtering rows where there was a relatively high amount of snook. We can look at that just to verify that we've done what we wanted to do. So 2 columns, high catch of snook. So this is all well and good. It works. It did what we want, but it's not really the most efficient way to do this. So we can use pipes to string these 2 separate processes together. So a pipe, so let me just copy this and I'll explain what a pipe is and what it does. So pipe is this guy right here, this operator that's percent greater than percent. This is part of a package that is loaded with the tidyverse that is an entire standalone package by itself, because programmatically piping is a little complex on the back end, but for you, it will make your life easier. But when you load tidyverse, you have access to pipes. So what the pipe operator is sort of syntactically like is sort of like and then. So when you're writing a pipe in your head, think about it like this. So here's fishdat, and then I'm going to select these columns, and then I'm going to filter. So it's linearly accomplishing all of these commands you did up here, but all in a row. So it's a more sequential way to write commands when you're wrangling, to write functions, because here we're doing it one at a time, where we're first selecting, we're making a new object, we're taking that object, and then we're filtering and creating our final object. Here we're doing it all at once. We're taking fishdat, we're selecting the column names, and then we're filtering. And we have only one object that we've created when we've done this. So I'll run that, and you'll see that it runs all at once. And when you're done, you've created the same thing that you created above, but now it's just a better, clearer way to do this. So the other thing to note is that when you are doing pipes, the first argument to a function is always going to be the thing that comes before the pipe. So if you look at the select function here, above, I had to specify that fishdat was the data set we're working on to select the columns. Because this is in a pipe down here, it knows that, okay, this is upstream of the pipe, this is downstream, so it knows that, okay, it's feeding this data object into the first argument of select. So we don't need to specify that because we're using pipes. So we only use in the select function the two columns that we want to select. We don't need to tell R to do this on fishdat because it knows. Same for the filter. So it's taking everything up here and using that with the pipe as input into filter to only select columns, or I'm sorry, rows where common sub count was above 25. So R just knows that it's just linear process of what's created prior to the pipe is used as input into the next pipe. So that's why this works so well. It's cleaner, there's less typing, and you're only creating one object. One last thing about pipes before I set you free on the last example. What's really annoying with pipes is that it takes 6 keystrokes to type them. So shift percent, shift greater than, shift percent, 6 keystrokes. That's kind of annoying. There is a shortcut in RStudio where you can get a pipe for only 3 keystrokes, Control-Shift-M, or if you're in Mac, Command-Shift-M. I think I've got that written down in the lesson plan somewhere. Yes, Control-Shift-M. So you can either literally type it out, which is fine for now because you're learning, but in the future, get used to using Control-Shift-M. And so that should be it about pipes. For this last exercise, we're good on time, so I'll set you free on this. Essentially, all we're going to do is redo exercise 4, but now instead of creating, here we created 3 different objects, actually rewriting an old object over and over. We're going to repeat this thing, but do it with pipes. So it should be fairly intuitive, I hope, and I'll give you 5 minutes on the clock, and then we'll discuss how that looks. And as always, you can cheat, but don't do that. All right, that's 5 minutes for exercise 5. Hopefully you guys were able to understand what you can do with pipes and were able to reproduce exercise 4 with pipes. What I'm going to do, we're almost at a break, so I will just very quickly show you how I would do this on my end. So this is example 1, which I had above right up here, so I didn't need to copy and paste that, but let's do this with pipes. I'm sorry, that should be exercise 4, technically. All right, so we'll say exercise 5. Now you could do select first with fishstat in the function, doesn't matter. I always like to do it like this with data first, just so I can see very easily which data set is starting this whole pipe. So I could do reference, sampling date. Also, tab completion is your friend in RStudio. See how when I type a column name, it gives me a suggestion which one I'm trying to type. If I hit tab, it'll complete that. And then sand sea trout. I don't think it works for the ones that have the backticks. So select, Control-Shift-M my pipe, filter, sorry, I don't need to do EX4 because it knows it's using everything above the pipe. And then rename date equals sampling date. So if you're hung up on this versus this, remember here we're testing for equality. Here we're just saying assign the name sampling date to date. So we're not doing a logical test to filter in the second one. So if that was a little unclear. So EX5, just for fun, I'm going to rerun the first example, and I can check with the identical function if EX5 is the same as EX1, and I get true. Hooray! So that means the pipes did exactly the same thing as what we did in exercise 4. So hopefully I've convinced you that this is a happy and better way to link your wrangling functions together. All right, so we're at a break. I want to say one thing that came up in the chat before we go on to break. Some people are having trouble importing the fish data. I'm not seeing it on my end, but I think some people were having trouble because the fish data CSV was called fish data with an A at the end, .csv, and I'm calling it fish dat when I import it. Again, it doesn't matter what you name it. I could call this data 1 or whatever, but just make sure the name of the file when you import it is the same as what the actual name of the file is in the directory where you have the data. So if you're seeing in your directory that this file is called data.csv, you want to type here data.csv. Otherwise, it doesn't know where that file is because there's nothing named something that's not there. But you can call this whatever you want. I just called it fishdat for name continuity with the name of the file. So with that, we'll go on break. We're going to start again at 11:30, and we will finish up with data wrangling.